There you go. Now we have sound. Everything seems fine there. Is everything fine with the stream? Obviously, I'm making some of this a little bit larger. Probably like this. Oh, the bitrate is super low. Hang on. Yeah, I'm gonna have to fix this. Bitrate should be higher now. Though it's still showing me a warning. But I think it's fine. Yeah, it's saying fine now, basically. So yeah, before it was 2500, and that's not quite enough. You could say. It's a little bit low, so I think we should be fine now though. And what about the volume? Is it fine? All right. Okay, so as the title says, we will be, in some ways this is going to be an experiment to kind of feel out some of the stuff that Odin has for dealing with large numbers and stuff like this. So for those who might not know what Diffie-Hellman actually is, it is a, well, it's used very often, at the very least, for key exchange between two parties. So, for example, a client might want to connect to a server, and we do not at that moment have an encrypted connection. And it might be that there is no public key for this server, so there's nothing we can use to encrypt stuff beforehand. We have no idea how to encrypt something between these two parties. So there's a process which we can go through in order to establish a shared secret between these two parties that we then can use in order to have encrypted content on this connection. And Diffie-Hellman is an algorithm or a protocol that can establish this for us, and so on. It is fairly simple, and we will be trying to implement this in a classic server client type way today. And it is, to some degree, it will be about effectively learning sort of, okay, because Odin, for those who might not know, has a big math module, right? Which we can use in order to generate very large numbers. So for example, we can generate a large prime that is 3072 bits in size, for example, right? And we will then use this in order to work with this and so on. So that is one of the keys here, is that this prime P that I have here needs to actually be fairly large. And so the purpose of what we're doing today is to see if we can do this in Odin in a reasonable fashion, and so on. So let's go over, I guess, the actual protocol and see what we can do with this, right? So one of the parties, or both, might establish a P and a G, where P here is a prime, which is I don't know what they call this in the protocol, actually. Let's call this just the prime. And a generator, G. From this, or after this, each side chooses a random number, which is their private key. I have labeled this PRK here. From your own private key and the generator and P, you then calculate a public key via this calculation over here. So we take our generator with our private key as the exponent here. So generator to the power of private key. And then modulo P. And then you send this to the other side when you've calculated this. And with that information that you're receiving from the other side, you then take your the other side's public key to the power of your private key modulo P. When you've done this, and both of you have done this with the others' values and so on, you will reach the same number. This calculation here will result in the same number. And the beauty of this here is that some of this information, of course, is sent in clear text, right, to the other side. But it is very hard with the information that is being sent. It is incredibly hard to actually brute force these values so that you can then reach this shared secret. The information that's being sent is the, let's say, the cheapest side of all of the calculations, right? And what we actually end up sending is not enough to actually brute force this in any reasonable way. This kind of, this thing, right? So that's what we'll be doing. Here's an example of how this can look. Sorry, I just have to check my phone real quick. Yeah, fuck that. And so the flow of this will be effectively something like this. So we have P is equal to 13 here, and G is equal to 5. We have Alice and Bob. Alice is going to choose a private key of 23. She will then calculate her own public key, and she then puts 5, which is our generator, to the power of 23 modulo 13, which is our P value, right? And gets 8. Bob is going to choose a private key of 17. He will then take our generator to the power of 17, which is his private key, modulo 13, which is our P, right? And get 5. They both send their public key to the other. So Alice sends my public key is 8. Bob sends my public key is 5. And now Alice can calculate the secret. 5 to the power of 23 mod 13 is 8. Bob can calculate the secret and get take 8 to the power of 17 modulo 13 and get 8. So they both have reached this secret value now, this shared secret, by only exchanging this public key, right? And so this is the idea. There's another example here, but it's the same. And this is what we will be implementing, and we'll probably do this via a state machine. So I have a very simple kind of, let's say, scaffolding here for running a server and a client. And what we will do here, this is going to be a threaded client, or threaded server rather. What we're going to do here is basically have some kind of state for a connection, right? So this connection is basically going to go through steps that mirror effectively the page I read you. So we're going to basically be saying that, oh, when we connect effectively, there will be some kind of expectation, right? And when a message, for example, a certain message is received, we will then change that expectation via data, basically. So we're gonna be, let's just say here, actually, let's rename this to thread state, because I don't really want to, don't want to muddle the waters here too much. We're actually going to call this client state down here, which is a union of things, presumably. Yeah. We're going to have to figure out exactly who is going to initiate what. Presumably, or I'm probably going to make the client initiate this so that the server can basically just sit there and do nothing. Which means the client is going to generate and send the two initial numbers. So we have P and G, right? And so that's probably what we're going to be doing. I'll show you the interface first for what actually happens in Odin. So we can start working on this run client function here, which these two programs share the same binary. If you pass server, it will start the server. If you pass client, it will start a client. So that's kind of the idea, at the very least. Here we're gonna say run client error. This is a union of several different things. We will deal with that, what that can be later. So let's see, you say return nil here. Yeah. So I'll show you the stuff that I have taken a look at first. So we have math/big here. And let's just sort of say, okay, the first thing the client does is generate effectively a p-value, right? So a prime. So we're going to say random prime error here. We're going to say big. And there's a funny thing going on here with the big module, where lots and lots of useful functionality is actually in quote unquote internal functions. I don't know exactly why. They're not internal. You can hide functions in Odin just fine. They can be local to a file, they can be local to a package. But in the big package, they're just called internal, but they're definitely public. Which is odd, to be honest. I don't know exactly why that is, but it is that way, basically. I don't know exactly what to think about this, to be honest, but yeah. So let's see here if we can, we're gonna take this here. We need an int value already. Yeah, so here we need random prime. Let's call that prime, just like this. And prime here is going to be a big int, like this, right? So this is actually a structure with lots of state inside of it in order to do things. And this is for big integer arithmetic, right? And so here we take a pointer to that because we are initializing effectively a big int here, right? And we're going to say 3072, I think that's the value we want. It doesn't matter so much, to be honest. Let's say 128 trials. I don't know exactly, to be honest, what these values are, what we should be doing here, to be honest, but we'll see. And yeah, let's let's leave this like this for the time being. The error we can receive here is a big error. So let's say if random prime error is not nil, and here we don't actually need to, no, we can do or return here, in fact, like this, because we're gonna just say, no, let's dress these errors up. I think it's fine to do so. If random prime error is not nil, we want to return unable to generate prime, for example. This seems like a fine error to have. And this is going to be a big error, like this, instead, of course. And so now we're basically saying, hey, I couldn't generate this prime, right? If we save now, what happens here? Error is run client. Sure, we're gonna print and exit if this happens, like this. If I say task dh client now, with 4200, for example, we should be seeing now that, oh, it's doing something, right? Note also how incredibly slowly it's doing that thing. Now the program finished. There's nothing happening in this program except this random prime, right? That is how slowly this 3072-bit number is being actually generated. And we could take a look here, you know, what does this, you know, what do different levels of optimization do for us here, right? So if I say here speed, for example, right, we might see that this is going faster. First, actually, let's not do that, but let's time this, right? So I want to. This is a good opportunity to show that as well, actually. So what we're going to do here is we're going to use the time module. Let's say before prime is time.tick now, and we're going to import time here, and then we can do after prime time tick diff, or prime time. Yeah, let's call this prime time. So prime time here is a tick diff. It will take the previous value like this. Or hang on. There is an actual tick. Let's see here. Tick since. Yeah, it's tick since. That's the one. Right. So now we're getting essentially just a duration for how long did this take? How long since the actual value here, right? And so here, what I want to do, let's just put that there. I want to just print this, basically. This is not going to be MS at all. In fact, this value here will be printed in whatever, like seconds or whatever it might be, automatically. So let's run that without any optimization first. And then let's run it with optimization and see if there's a difference. So this is a random prime number of 3072 bits. And it takes approximately 10 seconds. Right? And let's see now if we can so now the build, by the way, is going to take a little bit longer because we're actually optimizing. Not that long though, but we should see a difference in, well, hang on. We did not see a difference in this. Let me see if this is. Well, we didn't expect it to go slower. That's an interesting failure mode, to be honest. Okay, so it's random perhaps a little bit. Let's run it again and see what happens. I haven't tried this, by the way, running the random prime generation, like big int generation in optimized mode. Okay, so now 10. You can also actually use aggressive as an optimization level. I've never tried it. That could potentially be a thing. 23, okay, so it's very variable, is what we can see here, right? 23 seconds to generate this value. That's a long time. That is a very long time, in fact. Yeah, I don't know how I feel about that. That's, I mean, if I were to say like 512 like this, please tell me it wouldn't be long at all. Yeah, okay. 512 bits, not that bad. It's, you know, something you can do fairly frequently, to be honest. I say fairly frequently, but certainly not, you know, once per second or something like this. But okay, so obviously the bit value here is factoring in a lot, right? Now, what if we have, you know, we'd say 64 of these, this value here is trials, right? By the way, I found this interesting note in the documentation. This is possibly the mother of all prime generation functions. So someone is having a lot of fun, apparently. Oh, safe here is actually interesting, because this is one of the things you want for a lot of values, actually. Interesting. Now, it might be good for us to actually see, you know, what are these flags normally, right? What's the zero value here, right? All right, so the zero value is blum blum shub, I guess. We would want safe, probably. Let's try this. We've now pulled the trials down. We've halved them, right? So let's see what we end up with. This could, of course, have a large effect on the time needed, and we can see it does, right? 2.5 seconds, because we're doing 64 trials less, right? But yeah, these are large numbers. Obviously, you can see here that there's a large kind of, you know, this is a different range of actually, you know, random generation, right? I don't know exactly how fast this is supposed to be, but, you know, the only thing we can do right now is basically configure some of these parameters, right? And see, can we find some happy kind of, because we're testing stuff out, right? We have to, you know, turn the knobs a little bit on this and see, you know, what happens here. And then you would ask someone who actually knows what they're doing, you know, what are these actual values, right? What am I gaining here from my 33 or 32 trials, right? And so on. And this is something that the documentation might want to add, to be honest, right? But yeah, we don't have that yet, so, you know, it is what it is. Now we have our random prime, and we get this in approximately 1.2 seconds or so. I think that's fine. We're gonna do that for dev at least, right? I mean, in fact, we could probably just do 2048 with 32 trials. No real difference, apparently. Let's just go with this. Let's go with this. So we have our prime number. We're gonna keep the logging here just to see sort of are we finding in interesting cases, and so on. The idea now is that there is some kind of client state here. I'm gonna put this just above this run client function because that's where it will be used, right? So we're gonna have some kind of concept of, for example, right? Let's say awaiting public key. For example, let's say client awaiting public key, right? So remember, we have different steps here, obviously, right? Each side has some kind of expectation from the other, right? And one of these expectations is you calculate your own public key and then you send this to the other party, right? In order for us to kind of have a reasonable time here, what we're going to do is we're going to establish an order in which everything is supposed to happen, right? So the order we are going to be doing is basically the client connects and sends the prime P and the generator G, both of them. There's no agreeing upon some value here. We're just gonna straight up pick two random values and send them. That's how a session is going to be initiated, basically, right? Then each side is going to choose a private key, and actually we might make that a state, actually. Choose private key, like this. So that's a state as well, right? Our client can be in that state, right? So this is effectively a state that only involves us in some ways, but we're going to be basically having this function trying to go through these states, right? So here the client is awaiting a public key, calculate shared key. It's probably more or less what we want. Choose private key is really going to be an empty struct, I think, because that's kind of the only thing we actually need. Or we could store our prime in here along with our generator, which I suppose should also be a big int, actually. It can be a random number. It doesn't need to be prime, as far as I know. So let's see if we can find a function for that, actually, because we of course have a random number for our, internal random generator. That does not sound like what we want. Let's just say random. What is this random? Int random, right? Generator. And here we want 2048 again. Right, the trials have only to do with primes. This has no trial value at all. It's just a random number, indeed. Okay, that makes sense. Unable to generate generator is our error here. And so here we want generator, like this. How is everyone doing today, by the way? Right, choose private key is not defined. Oh, hang on. Choose private key, yes. This one. And then client awaiting public key. We do need to keep our prime with us as well as our generator. But here we should be also holding on to our private key, I suppose. I suppose this also needs to be a big int. That does not need to be prime, by the way, so we should be fine. And so calculate shared key should require all of these values. So let's see here. Okay, let's just see here that stuff is making sense so far. Okay, so the prime bit here is obviously a little bit, you know, it's a lot in comparison to everything else, right? I think the private key should be less actually than the prime, so we might need to sort that out as well. Let's see if we can find some kind of No, I don't think that there's anything here. We're gonna go with this for now. I'm not entirely sure how this is going to hang on, int random. Okay, so we have these two things now, and here we actually want to start connecting two things, right? Sure, we can have our client state. Let's call it state here. Is going to be. I'm going to do this for now. Like client state is equal to, and then choose. Yeah, choose private key. Actually, no, nil from the beginning. And we can then create this state. Let's see here, net dial TCP. And let's do an endpoint. We know exactly which computer we're supposed to be talking to, basically. This is a net IP4 address. Like this, and here we can get a dial error, obviously. Yeah, socket dial error, if dial error, blah blah blah. Right, so our socket is not used now. Let's call basically some kind of, let's say, handle session with our socket and our prime and our generator. Actually, that's a good idea. And here let's just do or return here. Yeah, let's do or return. And then in that function, we'll actually do different things, right? So handle session is a procedure that takes a socket, which is a net TCP socket, obviously. Prime, which is big int. Here we can do prime and generator like this. And returns a client error. What did I call it? Run client error, like this. Yeah, that should be fine. Missing return statement, that's fine. Okay, so the client flow of this, right, will basically be the state here is going to be right. We don't need state out there. We can actually make the state in here instead. We have some client state, which is equal to choose private key. No. Once again, let's leave this for when we actually have something. Oh no, we can definitely choose private key here. This is the state we are in fact. So let's see here. Choose private key, client awaiting public key. Choose private key is maybe not even relevant. Send prime and generator, right? This is the actual purpose of what the client is supposed to be doing, right? So that's more accurate than anything else. This is going to be what we have: send, prime, and generator. And this might not take any arguments. I suppose we already have access to those, so we might not need to actually have that in our data at all. Likewise here, we might not need these to be in here at all. Also, we could make these empty structs basically. Normally in certain languages I would certainly make them like this, with the values inside and so on. But here we can we should have access to all of the stuff really already, I suppose. Except here, public key, server public key, which is a big int like this. So now we have our state. This is our client state. Let's see here if we can sort this out. A big for, not that bad of an idea. We will see how this works. Switch S in state. If we have send, prime, and generator, we want a certain behavior, right? If we have client awaiting public key, await. Let's make these in the imperative, all of them. Await public key, calculate shared key, send prime and generator, await server public key. That'll be fine. Yeah, okay, this is fine. When we are in this one, send prime and generator, right? What do we actually want to do? We want to let's just do this kind of implicitly. We're not going to make a protocol with tons of codes and so on. We're going to essentially just say, you know, there's an implicit flow here that we're following. Very little kind of error handling built into the protocol, right? So what this is going to effectively be right now, we could assume 2048 bits on both sides. In fact, this wouldn't be that bad of an idea. But better than that could be if we actually, in this state, what we do is we say bit size, right? Let's say bits. I think there's a count bits. I think that's one. So here we have bits, prime bits like this. If we take count bits here, this also has to be pointers, by the way, like this. And here we should have an int, right? So what we're going to be doing is we're going to send this. Yeah, we're going to send this to the other side. Here's how many bits are going to follow, right? And sure, unable to count bits seems fine. We're going to have to create that error, obviously. Bytes, hang on, there's no big bytes, right? Size in bytes. Oh, hang on, that's probably the one we want. Let's do bytes like this. Yeah. Yeah, okay. And now we're going to send this value to the other side. So that will be net send TCP. This takes a socket and of course a bunch of a slice of bytes. So what we can do here, we know that this should be an int. We could just straight up say, you know, this is a size slice we can transmute this here. I think that should be fine. And then now we can send size bytes here. This should also have a send bytes sent and send error here. We can actually kind of ignore this one, I think. And here we want unable to count bits. This should be bytes actually. And unable to send prime. Yeah, let's try this. Hang on, it's not mem copy we want there actually. now let's see here, size byte, sure that one is fine. Hang on. Yeah, this is not gonna work here. Oh, hang on. Not len. Await server public key. What did I? This one. There you go. So what should happen now is we connect, obviously, and then we go into this handle session function. We have a socket, we have a prime and a generator already. We generated that as the client, right? Our state is set to send prime and generator. And so we should be going straight into this here. And we should be sending, this is how many bytes you are going to be receiving, right? Which leads me to believe maybe send, yeah, hang on. Send sizes is actually what we want here. Yeah, bear with me here as we figure this out piece by piece. Send sizes is going to be a state before everything that basically, in some ways, it's the first thing that happens. It's the client telling the server, you're going to receive two things here, two integers. And those integers are going to be describing the byte size of other values, let's say. Yeah, I think that will work fine, which means also we have generator bytes, we have this, and so on. Byte count error is not gonna work here, actually. Yeah, generator byte count error, like this. Unable to count bytes, sure. And unable to send prime becomes unable to send sizes instead. Right, so now we have an unhandled switch case, and that is of course like send prime and generator is the one that comes after here, right? Let's just see that stuff kind of makes sense-ish. So we have task DH server on 4200. Task DH client on 4200. Now, of course, I'm not really printing much, I suppose. We could just sort of make sure that the server here is receiving clients as it should, and so on. Let's do that. We're going to, in handle client, we're gonna print, let's just print the task, to be honest, right? So, hello, Borhen? Is that how you said his name? Let's see here, thread state is going to be task.data cast as a thread state value, right? So task data, for those who might not be might not remember this, this is basically a row pointer, right? It's what's being passed in this here. So you have this thread state that's being passed to handle client via the pool, right? And so this is what we have here. Right, so now this is the server bit here, right? And let's just say context logger, log create console logger, like this. And log debugf %v handling client, like this, right? With our thread state, like this. Let's just do this for now. We'll see that something connects. We'll see that, you know, something is happening, right? Also, we could add a read here, actually. And so here I kind of want to say state, which is server state, that's a good guess, is await size. I mean, why not, right? Await sizes. That is certainly mostly reasonable, right? So if we say server state here, we have await sizes, we have await prime and generator. Yeah, that comes after we have received our sizes, right? And then we have await client public key. We probably should send our own public key at some point. We can do that when we send server public key. Let's add that one. There's no real problem with being too verbose with these states. You can modify them over time, obviously. Await prime and generator. This is really just a state, much like in most of the others where we have empty kind of. It's just we use this just to talk about the state. Some of them might hold stuff for sure, but not right now, maybe. Awaiting client public key, sure. Send server public key. Yeah. This one we could actually say server public key like this. I don't think that's a bad idea, actually. And we don't need in send server public key, we don't need this one necessarily. In fact, here we could put prime and generator as well, because we're supposedly receiving them here, which is when we transition into this state, and I'm going to put those values in there. So we're going to see both parts of this. Send server public key. We also need a private key, in fact. Let's do server, calculate this one. They've ended up with the same names, obviously. So in the case of the server side of this, the handle client function, right? what actually ends up happening is that this state value here ends up being a bag of values that basically holds values across different state transitions, right? In the other case, in the client side, we didn't really need this. We had access to most of these values. I mean, unless it's potentially it's the case that I'm missing something, but we will see, I guess. We might have to hold on to values there. The most important bit there is that we can handle this however we like, right? For example, we could just say, hey, my private key is allocated up here, for example, right? And that's trivial to do, of course, right? The shared secret could also be here, right? And so on. And we really mostly need to fill that value in when it starts existing or whatever it might be, right? So let's do that for here. We could do the same for handle client, actually. This might obviate the need for some of these things here. Yeah, let's try that actually. So here we're going to remove all of these. Actually, in fact, I could just straight up put this here. And here we don't need these prefixes now, really, right? We have a private key, we have a public key, the client has a public key, we have a prime and a generator, right? These are values here. And now we can actually reuse calculate shared key. We could also await, we could actually say await public key, right? So if I say await public key is a structure like this, we can actually reuse this in both of these, because of course the client should also be awaiting a public key like this. And now we're going to be reusing that one like this. Yeah, private key, shared secret, declared but not used, not the biggest of deals. Await public key is what we want to do there. Server calculate shared key does not need to be that one. We're gonna comment those out for the time being. Unhandle switch cases, and that's because we don't have this one anymore, and we don't need this very specific one there. Right, so now we have kind of set up skeletons for both of these state machines on either side, right? So we have the client with its await sizes stuff here, and so on and so forth, or the handle client. This is the server side, sorry. Here, what we want to do is read two integers, basically. Yeah, so let's just read. Let's exhaust whatever is being sent, first of all, here, right? Let's see here. We have a receive buffer, first of all, probably, that we want to use in many cases. We're going to say mem kilobyte times 64. And here I want to net receive TCP with our thread state socket, certainly. And here we're gonna pass the buffer, our receive buffer, like this. And of course, what we could do here is what it was doing here was basically saying the sizes of, you know, these values, right? So we could say only use the first 16 bytes. Absolutely, we could do this. We could try doing this and see what happens, you know? So here we're going to say n and receive error, like this. If receive error is not nil, log error f, sure. assert n equals 16, and here I want to say tprintf yeah, let's try this. Starting the server, starting the client. In the client, of course, it's much slower here. Let's see what happens. Okay, so we received 8 first. And that is, of course, because we have 2 sends here, presumably. And we only really need 1. I don't know exactly why I did this, but let's just do okay. Let's say send buffer here. In fact, let's establish a send buffer up here, which is 64 kilobytes. And then what we can do, let's say here, size bytes here, sure, that's all fine. We're not going to send here though, right? We're going to say prime size bytes, and then we have a generator size bytes, which is actually a new value here. And when we have those 2 things, we can copy into our send buffer from the beginning prime size bytes, and then another copy with our generator size bytes, right? And here what we're going to be doing is we're going to take the send buffer and simply send the first 16. I think that should be fine. No procedures. This usually means basically we have some kind of, oh, hang on, this is not how it's done. Undeclared name sender, that's fine. There you go. Let's start the server on the left side and the client on the right side. Oh, I'm not showing what I'm not showing what I'm receiving. We're passing this assert here, and then we're not really doing much of anything. So let's just say debugf here received sizes, right? And here, what we can do here actually is we can say prime size is an int, generator size is an int. When we receive these 2 values, what we can actually do, we should be able to do, let's see here. We should be able to take, hang on. We don't have an array here, it's important to understand. So what we do have, yeah, the problem, okay, so I'll show you what I mean by this, right? So this transmute here can't actually work because the thing here is a slice, right? This slice is actually 2 values. It's a size and a pointer. So you can't just take that like this here, right? That doesn't actually work, but we can, let's just say this instead. prime size bytes is actually 8 bytes like this, right? We copy into prime size bytes the first 8 bytes of our receive buffer, right? Then we can set prime size here by transmuting the bytes into an int value, and that's it. We do the same for generator and so on. Here we don't actually need, we don't need a separate, we can just say size bytes here, for example, like this. But let's just leave that for, you know, like this. And now this should set our generator and our prime size. And I want to output those like this. We're going to say bytes. Opa. Okay, yeah, that's a little bit of a loop. We are never going into any other state, so that would probably be a thing we would want to take a look at. So let's say state here, right? We want to actually set our state now to await prime and generator instead, right? Now with this we should then see that, oh, the server is basically receiving these, printing them, and moving on to the next thing, right? So here we can see, okay, we're handling a client, we are receiving some bytes, and here we are saying, okay, these are the values we received. Forgive me here for just real quick. Just had to check that these values made sense. They do, so that's fine. Let's see here. If we log this as well, we'll just, it will be better this way probably. So we have our prime size, our generator size at this point, right? And let's see here. We want to await this prime and the generator, right? So let's uncomment those and receive those as well, right? And we're going to receive this into the appropriately sized sort of slice here, right? And so this is going to be n and receive error. Sure, that sounds reasonable. Net receive TCP, thread state socket, and receive buffer here. We can slice into it exactly the value that we need, right? Not that we have to do this, but you know, it's a reasonable thing to do. N is equal to the prime size and generator size. Sure. Sure. That assert is mostly reasonable. I don't have any. We're not going to be able to necessarily print. Actually, let's. Okay. Now let's not print those. I will sort this out anyway. What we actually want to do here is we don't want to do this like we did the others. We don't want to transmute anything. There are special functions for dealing with these, in fact. Int from bytes and so on. And here's bytes big, and we're gonna see on the other side that we also have to use big for this as well. We could also say little. Let's just do little endian, it's fine. And this takes a few values. It takes the actual int to fill in and the buffer to fill it in from, right? And here we actually want to fill in our prime. That's the first thing that we actually are receiving, right? And this returns a big error again, right? So bytes int from bytes error on this. And sure, we can do this perhaps. Yeah, sure. I think that's fine then. And here we could try to print this. I'm gonna print it so you can sort of see what it actually is. There's almost no useful information in there, but it's fine. So here, let's just double check this. We're filling in the generator after, of course, so that they're sent in prime and generator order, right? Then we have the receive buffer here. We go from prime size to prime size plus generator size, right? That makes sense. And when we've received these, we're gonna print that as well, and then we're gonna await the public key. And here we should calculate our own public key as well, or yeah, we should calculate our own public key. Let's see that we sort that out here. So public key is now uncommented. Public key, I don't remember this. We have this calculation, the generator. There's actually a special, so I'm going to copy this so we can actually see this in action, because I do want to show you guys this. I think it's interesting, right? Because of course these modules exist for a reason, right? So if we say big here, I'm gonna paste this here, right? This is the actual calculation we have. Some g to the power of our private key mod p, right? And this actually reminds me we need a private key at this point, right? And we need to calculate that as well. Private key, let's uncomment that. So let's say here that big internal random private key, I think it's actually int random. Yes, it is. And here we actually want I suppose we want 1020 or 2048. And we could take effectively, we could just say prime size times 8, like this, right? And here we could say private key error if, like this. Now we have our private key, right? And we need our private key for this calculation here. We have our generator at this point, certainly, we should. And then we have P as well. So what we can do is we can do this exp, let's see here, internal int exponent mod, right? So this function here, right, does stuff. So you can see here, it computes a result, and that result is going to be equal to g exponent x mod p, right? Which is suspiciously close, of course, to what we need, right? So res here is our public key, right? And x is our private key. So what we're going to say here is that res is equal to a pointer to our public key, right? G is equal to generator. X is our private key, like this. All of these are pointers, by the way. And P is equal to prime. And here, of course, I want X is equal to this one, right? And here we can say exponent error, like this, perhaps. And we're gonna just load this and say like this. So what this is going to do now is fill in this res with the result, right? So it's filling in this public key. Hello. Hello? If you could elaborate, what do you mean by what exactly? Let's save here and see if stuff makes any sense. Await prime and generator. Note we haven't actually sent anything from the client yet, right? So await public key. Okay, so we have await public key, of course, after await prime and generator, right? And when we get await prime and generator, we actually say, hey, now I'm waiting for the public key. And when we receive that, we're going to go into send server public key. Okay, I think that's fine. That's mostly fine. Let's see if we can run this at all. Actually, let's implement a little bit more of the client, I think, to be honest, right? Because we've done a little bit of the server here. Okay, we have the prime and the generator at this point, and so on. Let's see what the client is actually going to be doing here. Send prime and generator is what we're going to be moving into here, right? So we're moving into that state. Private key, shared secret, server, public key, also we want here. And this one does not need to be here if we do that, basically. Calculate shared key. Yeah, we don't necessarily need that one either, to be honest, but it doesn't matter. Send prime and generator. This is where we are now, right? So we're going to be moving into this state. We have our prime and generator at this point. They're all fine. They're already established at this point. We generate those when the program starts, right? So it shouldn't be really much harder here. What is going what is going on? Secure my crypto assets in Gmail before I take them to the bank. Is that what you're trying to say? I don't know what you want, to be honest, by saying this, but this is just a random programming stream. I don't think I can help you with your crypto assets, to be honest. I can probably help you get out of crypto. That's the first step to probably a better life. If I had any advice, it would be don't secure any crypto assets. Get rid of them as fast as you can. Probably. Today, tomorrow, I mean, good luck. Depending on where they are, they might not even give them to you. In reality, if you want to withdraw them, I mean. But yeah, this is not some kind of crypto stream or whatever. I don't think that there's even a measurement for how little I care about crypto, in terms of, so if you have any questions about programming, I'm all ears. But yeah, crypto assets and stuff we can leave that some other place, So we're gonna send our prime and our generator here, right? Which means we're gonna have to on this side we're gonna have to turn those into bytes, right? And so that's a little bit of also kind of an involved process. But let's look at this, right? So here we're going to say prime bytes like this, right? And we're going to say int 2 bytes little, right? Because we said little on the other side, so we need this to be little here as well. Take a pointer to our prime. And yeah, here we actually need to fill in a buffer, actually. So we're gonna say send the buffer from the beginning, like this, right? This returns a big error as well. Int to bytes error, let's say this, just for now. And if that is unable to send prime. Hang on. And generator. Well, let's just say this one. Well, actually, not super clear on unable to make int bytes. Let's just say this one. I think that's fine. Here we want to also take the generator, of course. We don't want to actually, so here we actually need this to be we need this to be after the other bytes here. Okay, what are you trying to say in the chat? I'm sorry. Want to listen to bad talk, clean my ears. What does this mean? What is even happening? Like, what is going on? So here, what we actually want to do is probably we want to keep the count here that we probably. So we used this before, right? We said the prime size, right? So here, I think it would be reasonable. Yeah, let's save our prime bytes, right? Prime byte size, like this, is an int, and generator byte size is an int as well. We're gonna save those from what we did previously. Yeah, I think that prime byte size is, dude, it's just this, you know? What is Copilot even doing? Now we're gonna save those across different states. Right, and this is where putting some of your state variables in the actual states themselves actually helps a lot sometimes with this type of stuff, right? Because you don't jump, you kind of just use the data you have at hand instead of constantly dealing with sort of, oh, hang on, let's add this outside of the loop or whatever it might be, right? So it can be a little bit easier because you know exactly where you get all of your actual state from, right? But it is a little bit more natural for functional languages, I will say. And here, again, we want to actually prime byte size, like this. I think this should be fine. Yeah, we won't know, to be honest, so it's fine. Now we want to send both of these, right? So we have send here, net send TCP, socket, and here we could, I mean, yeah, this should work fine. We're gonna send as many bytes as this should be, you know. In fact, we could say prime byte size here as well. And here we could, to be completely clear about it, just do this as well. If sender is nil, unable to send prime and generator, that's not a thing anymore. Unable to make int bytes, it's not a thing as well. We're gonna make both of these. Private key declare but not used. Let's comment these out just for the time being so we can. Prime is a right. It's already a pointer, I think. Yes, it is. We don't need to take a pointer to that. Into bytes little. Into bytes little. We don't need that one to be a pointer either. Right, unable to make int bytes, we never added to our union. Like this. Now we're fine. I mean, fine for just in terms of compilation errors, obviously. And here, we know that the other side. Oh yeah, we are almost at 500 subscribers actually. Actually, I might, let me see here. Yeah, here actually, we are at 499, in fact. So that's cool. So when we have sent our prime and generator, right, what is the other side actually doing? I suspect here that the other side is going to be, here we have await prime and generator, right? We don't have any state after that, but we are saying await public key here, right? So we probably want at this point, we are gonna await that public key as the server side of this, right? And here we have this state for the clients, right? And we want here to calculate our own public key and send that probably. I think that should be fine. We're gonna say for now though, state await public key because I want to test the stuff that's happening so far because there's no telling what has gone wrong here. Okay, stuff seems to have happened. To be honest, there's not that much going on. We received, of course now this is all, you know, because the font size is so massive, we can't see much, but we can see here, we received the sizes that we needed, right? And then we can see here, we received prime, right? Our prime number from the other side. And you can see here the internals of a big int. You can see that the digits are stored in a dynamic array. You can't see that it's a dynamic array here, but I'm telling you it's a dynamic array. And this dynamic array has digits basically in packs, right? And so on. And yeah, this is basically what a big int is in Odin, right? So let's see here. We are receiving these, and that's on the server side. The server side is saying receive generator. It generates a private key. It then calculates the public key. Here we could send, in fact. Yeah, okay, so we're gonna send from when the server receives this information. It will pick up private key. It will it will send its own public key that it basically calculates here, right? And then it will await the public key. Yeah, I think that should be fine. So we're gonna send that here. We're not gonna log that, I think. Let's do that, to be honest. There's no problem with this, to be honest. Let's just do this inline. I don't know that it's super, not all of it needs to be, you know, hey, this needs to be its own state. And you can always add more states. Like I said before, all of this is, you can add it whenever you feel like you need to. And here we actually want to say send buffer and up to prime size, like this, basically something like this. This here is going to be just underscore send error, and I don't think we have that yet, so it's going to be an actual declaration as well. And here, of course, we need to fill in the send buffer with stuff, right? So this is, you know, important. We have our big, right? We're going to say int to bytes little, right? So here we are taking whatever we need to write, like the actual public key, right? So we're going to take a pointer to public key. We're going to say send the buffer up to prime size. So that's the area we're filling in. Yes, that seems to be fine. I have no idea. I'm probably gonna have to time you out or something. Shy full or whatever. Because honestly, none of this is making any sense. Ironically, I think the part about crypto assets made the most sense, you know? So that's a bad review here a little bit, I feel like, because that shouldn't make sense, to be honest. But so, like I said before, if you have questions about, you know, programming or what we're doing here, you know, and so on, that would be cool, of course. But if you have just random words and weird emojis or talking about cryptocurrencies or something, feel free to leave, because yeah, especially the crypto part, like just move that elsewhere. And also weird emojis and just saying yes or the word data or whatever the other stuff was, you know, just don't. So, into bytes error. So now we're going to send our own public key, and then we're going to await this here, basically. That's the server side, of course, right? Send buffer. The server doesn't have a send buffer, guys. Why didn't anyone tell me this? Right. So that's all fine now. This is going to go into await public key, where it then will receive that public key, right? So here, we already know the prime size. We're gonna just go ahead and say that you always receive that amount, to be honest, right? So we're gonna receive TCP here with our socket and our receive buffer. And we're gonna do prime byte size, like I said. And here let's just say underscore receive error, if receive error, blah blah blah, unable to receive public key. Sure. That's not an error we have yet. We're gonna add that. That's a network error as well. And we're going to add that to our union because we remember stuff like that sometimes. Undeclared name. Client doesn't have a receive buffer. It only had a send buffer. And so now this of course has to fill in the server public key, which we should have yeah, we do have this here, server public key. And we also have never actually, hang on. Did we never? Right. We haven't calculated our own, we don't have a private key yet. Which we could actually, we could generate this even before we enter this function entirely. Because if we look at our notes, we'll see that the private key is just a random key. Right, so I'm probably gonna do that instead. Private key is going to be a pointer to a big int here that we are passed, right? So when we do handle session here, we're gonna say private key. And this is going to effectively be the same as the others. Before private key, like this and this. Unable to generator, generate generator, no, not really. Private key. And that's all fine. Yep, this should be fine. So now we have that value because we can do that value as early as possible anyway. So this will happen even before we connect to the server. And then we have the server public key, which is what we're going to be filling in now with the information that we receive from it, right? So we should receive a bunch of data here, right? And we're receiving this into a buffer, prime byte size here, right? Of that magnitude or whatever, right? And here we're going to say, sure, let's just double check here that stuff makes sense. We're taking a pointer to server public key. This is what we're filling in. We're taking the buffer. We're taking, of course, only the part, the appropriately sized part, and so on. And that's fine. If this has an error, unable to make int bytes, I'm not super upset about that. It's not super, yeah, it's not necessarily the most descriptive error for this section of the code, but you can always modify this after, so it's not a big deal. We want to go into the calculate shared key here, but we do have to send our own public key first, because I don't think that we do here. In fact, we don't have any space for this. No, we are definitely, yeah, we have to, when we receive the public key from the server, we should send our own. So that should happen here, right? So to do send public key. I'm going to put this here just for the time being, and I'm going to take a little break and just walk a little bit. I will be back fairly soon. I'm going to put just a be right back thing here. Let's see here if I can edit this also. Opa. I'm just gonna do this. There you go. All right. Let's see here. I'm back. Right. We are sending our public key, which we should have calculated all. We need to calculate our private public key, basically. Let's see here. Right, we have our private key. We need to calculate our public key. Right. So we need to generate that here, and the public key is of course here. Our generator to the power of our private key modulo p. So let's see here if we can say big internal int exponent mod, etc. The result is actually going to be res equals public key here, right? And the g is our generator. X, which is the exponent in this situation, right? Yeah. And our p, which is our prime. Like this. And I don't know here that we need this, to be fair. Let's see what it says. Cannot take the etc, right? Because these are already pointers. They are input to this function. So int exp error is this. Unable to calculate public key. Hello Max, what's up? So unable to calculate public key is going to be an error here. Let's see if we can just slot that into everything else. Private key time declared but not used. Sure. Let's just do this as well with that one. Not a big deal really. And here we want to actually send this pretty immediately, right? We're calculating the public key and then we're basically sending it straight to the other side, right? So I'm going to do the same thing I did before. We're going to use this line here, and I'm going to put the normal stuff there. But here we actually want to turn this into bytes, basically like this here. Right? So we take the public key that we actually calculated now, or and then we put the result of int to bytes little, again little endian. Hang on, I'm just gonna spam a little bit. Sorry about this. Just waking up. Gotta love the weekend. Indeed, yeah. Hang on. What time is it where you are? Yeah, quite the weekend, I would say. Probably, right? Because you are where exactly? I mean, not exactly. You don't have to dox yourself. But in time zone wise, right? Are you in California? Oh, 10:21. Okay. Yeah, that is quite the difference. Let's see here. This of course needs to be a pointer because we're, they're always pointers, these big int values. Unable to send the public key. We want to add that as an error. We have big old list of errors. So now we have sent our public key. Everyone really at this point from the client's side should have everything they need. Now I'm curious if we can actually, now we comment out shared secret here, right? And we actually do an int exp error, whatever the fuck again, right? We fill in shared secret, right? And let's just double check this, right? Because we never know. Copilot is fucking crazy sometimes. The shared secret is calculated with our public, the other side's public key, right? To the power of our own private key, modulo p, right? So this here is the G, right? This here is the X, right? So X should be private key. G should be the public key of the other side. And then modulo P, right? So, right, server public key, that's G. X is our private key. And P is, of course, our prime value, right? Unable to calculate public key. Oh, that's already an error. That's nice. I foresaw that, apparently. And now we have the shared secret, presumably. So let's log that. Now, actually, we haven't done any logging in this function, and we don't really even have a logger. So I'm going to say log create console logger here in the beginning. The client, we don't log anything on the client actually, which is interesting. So calculate shared secret or shared key. Shared secret is actually what this should be called. We're gonna do this calculate shared secret there, and this one like this. Now both clients or both sides of this equation should be well aware that this is the case. In await public key, of course, we do need to receive the public key that the client is sending, right? Send server public key. That one is not needed. We're already sending that one, so we can remove that one. That's one step less. Let's see here if we can clear out some of this. Here, await public key, that's of course the client's public key that we want to fill in, right? So it's essentially the same situation as we saw before. We're gonna be filling that in from the buffer. And effectively this code, we can accept this for now and see, you know, that it makes sense, right? So we're receiving n bytes here. We're saying, okay, received from the socket up to prime size, right? That is effectively the size of the numbers that we're dealing with. Then we're asserting here that, oh, we have received that much, and that's just a good thing to have right now. So that's all fine. And then we have this int from bytes, right? And this is int from bytes little. We have standardized on basically sending little endian values. We're filling in the public key here, right? That's not quite correct though, right? It's actually the client public key that we want to fill in. So if we look at the top of this function, right? We should have this, which I've commented out before, client public key, right? That's the thing we're filling in, because that's of course the other side of this equation. It's their public key that we want to fill in from the network. And so then here we're all fine. We receive a public key, calculate shared secret. This is going to be effectively the same as our other code, really. We are going to take, we're going to fill in shared secret, and we are going to take, so G, remember, is the actual how do you say this? The thing that's being exponentiated, right? X is of course the exponent, right? And that is our private key. We're taking the other side's public key and we're taking that to the power of private key. And then P, of course, is modulo P. That's our prime value, right? Error calculating shared secret, and so on. That's fine. Let's see here. Shared secret does not exist, of course, because I haven't made that in that scope. Shared secret is a big int. I'm gonna put that there. And now, of course, we probably missed a step or 5. It's fine. We will deal with it as we can, you know? So here, let's start the server and start the client. Unable to connect, refused. Why? There you go. Shared secret is, let's see here. Right, I'm just printing a bunch of stuff. That's maybe not what we want. Let's actually print this as an int value or something like it. Right. We could actually print this in hex, which would make it perhaps a little bit easier, maybe. But let's try for the moment, see if we can find something that makes a little bit more sense than this. First of all, int 2 is a good source of, you know, what can we do here, right? We can produce a string from it if we want. We could print that, certainly. Yeah, let's do, we can't do bytes, but let's do string here, right? So we're gonna take the shared secret, and let's see here, radix is 10 by default, 0 terminate false, not really super concerned. Shared secret string is this, right? And this allocates presumably. Let's see, this is an error, which is a big error again. Int to string error, like this. Unable, well, unable to print shared secret. Otherwise, we're gonna log this as a string. Like this, right? Yeah. Now, we're not guaranteed to, of course, be making any sense of this from the perspective of, you know, can we read this shit? So we'll see how that goes, to be honest. Here we can basically copy the other code almost verbatim, right? So we should be fine. Let's try this. Now, remember, the idea is here that we should end up with the same shared secret despite not sharing all of the information between these two parties, right? That's the whole point. If we do, we have succeeded. I'm foreseeing that something is going wrong, to be honest. Shared secret is 195.12, etc. We end with 671. We've done it. We have done it somehow. I'm actually surprised that this worked. You can see here that these, actually I have found out a way maybe we can print these that makes sense, or we could actually compare them very easily. But yeah, so anyway, I think we can say, because we start with 195.12493, 195.12493, etc. And then we end with exactly 44.58.671, 44.58.671. We can probably assume that these are the same now. So basically what we've actually done is we have implemented this, right? And of course, looking at this, it seems ridiculous how we ended up with so much code, right? But remember, like, a lot of this code is really dealing with the fact that generating these numbers is an error-prone and tedious process. We have to turn it into a slice of bytes over and over. We have to read from the network and so on, right? There's lots of code that goes into basically doing those things, right? But the important part here is we have done this, right? We have in fact implemented some sense of a protocol, right? So remember in the beginning I said we're going to make state machines, right? In order to model this relationship between these two parties, right? And that is what we've done here. The server state has a sense of order, right? It waits for the client to send the sizes of these things, right? Then it waits when it has those things. It says, or it waits basically for the client to send the prime P, right, and the generator G. Then it waits. When it receives these values, it sends its own public key, and that is not encoded in the states here. But we could say send public key. This is a valid thing to do, and probably I would do this actually in the end, because it would be reasonable to have a state that is specifically dedicated to we are now sending, right? So otherwise that is left implicit, and that's not necessarily what we want, right? It is fine here to have an extra state that simply says, hey, here's where we send our public key, right? And it is fine to just add more and more states. Remember, these don't take up any space. A union is going to be sized as the size of the tag, right? The size of the tag is usually some kind of integer, right? Which means it's probably 8 bytes or something. I don't think that they actually do 32. 32 bits, that is. And so it's going to be that plus whatever the biggest payload of any actual state is. And you can see all of these are empty. They don't have a size. They're empty, right? So adding more here is a question of simply, what do I want to be reading, right? What do I want to be reading in terms of code and in the cases and all of these things, right? And that is fine. You can just have, send public here. So if we were to do this, right, await prime and generator, let's find that one. We can see here that await prime and generator ends with, let's see here, it ends with a lot. We calculate our public key, and that's fine, but what I actually want to do here is I want to take this part here and say, no, we don't go into await public key here. Instead, we go into send public key, like this. And we copy that code here for sending this stuff, right? Like this. We say case send public key. We copy that code in there, right? Now we split this up into its own separate case, and here we go into state await public key. And of course, now you can see the shape of this is such that, well, a lot of these could be their own functions or procedures, in fact, right? And that's fine. Absolutely, you should do this, right? We don't need to do it. I'm a very big proponent of simply abstracting away stuff when you need to, instead of doing it prematurely, which I think is usually the case. So here we now have send public key here, right? And probably we want just send public key here, like this. And that's all fine. We've now added a new state, right? We can see now, we can see the shape of these states. As you kind of flesh them out, you will basically have a more, you will get more, a better overview of what is going on in your protocol, right? So we await sizes, and then we await the prime and the generator to be sent. When that's done, we send our own public key, and we await the public key of the client, right? And then we calculate our shared secret. And on the other side of that equation, right, we have this state machine. Where do I find this? Client state. We send our sizes. We send the prime and the generator. We await the public key of the server, right? And then we calculate the shared secret. And this is basically the order of stuff, really, right? It doesn't really get much more complicated than that, right? And this is effectively mirroring what is supposed to happen here. It's just that we have put an order to it, right? What we have done is we've said that the protocol does stuff in a certain order, right? The client is expected to send the byte size of the prime and the generator, right? P and G. The prime, or the client, is producing these initially, right? They produce P and G, and then they produce their own private key immediately. So as soon as they enter the conversation, they have P and G and private key on their own side, right? And then they send these values, right, to the server. So the server now says, oh, I am going to generate a private key, and I'm going to, let's see here. So we send sizes, right? We send the prime and the generator. Then we await the public key of the server. So it is now the server's time to send its own public key, right? And here we calculate our own private key, which we could make a state for. And then, actually, in fact, I think we should do that. Case calculate public key. Do I have that one? I don't think so, right? Yeah. So now we can see in the client, we have an order to things, right? We send stuff initially, then we await the public key, then we calculate our own public key, yeah, then we calculate the shared secret. And when we run this, we end up with a flow that basically, yeah, it works. We get the same shared secret. So the idea here between Diffie-Hellman key exchange is simply share as little data as possible between the two parties, right? We agree on P and G. We send this in clear text, right? Plain text. Then when we have the public keys of the both parties, right? These are also sent in clear text, just in the plain, right? There's no encryption going on. With these values, because we're using exponentiation and modulo, right? It is exceedingly hard if you use appropriately sized values. It's exceedingly hard to actually brute force this so that you could then end up also getting the shared secret based on these values that you can see on the wire. And so this math basically works out such that we can generate a shared secret that we both know, and even though someone else heard us say these public values, P, G, and the public keys, we actually end up with the shared secret much easier than they would, like computationally, right? And then what you do with this value, right, is you can use this then to generate secret keys, right? So this is a shared secret, but generally speaking, what it's used for is when you've done this dance, right? You have now your value. You can then use that value in order to generate keys of different varieties and so on, right? And this is used, you can use this now for symmetric encryption, which is we have one key that encrypts and decrypts, and it's usually a reversible operation. It's also considerably faster than asymmetric encryption and so on. So, to summarize, Diffie-Hellman key exchange is useful when you do not have any pre-existing ways of encrypting something, like asymmetric encryption with certificates and public and private keys, right? You don't have any pre-existing values for this, right? Which we would if we had RSA or some stuff like this, right? And we are coming into this without anything, but we can establish a shared secret which allows us to set up basically an encryption on this channel when this process is done. So yeah, honestly, this kind of was done faster than I thought, which I guess I'm saying a lot nowadays. But I fully foresaw that this was, we were gonna see that, hey, this is actually completely wrong and it doesn't make any sense, whatever, right? But it does make sense, in fact. So yeah, we have ended up with something that makes sense, and I'm very happy about that. So yeah, that's really about it for today. I'm gonna chill out a little bit, probably, with you guys. If you have any questions, that would be really, it doesn't have to be about this, what we did, now. Feet implement basic Diffie-Hellman key exchange. So yeah, hang on. I didn't address this before. I saw what you wrote actually, but I guess I was deep in just trying to make stuff work. Taiwan. Yeah, I imagine like Taiwan must be, how many hours? I guess you're technically behind in some, you're ahead, but it's in time zone wise, of course, like it works out like, oh, your friends will get up earlier than you and so on, like US friends and so on, right? Yeah. Cryptography and stuff, right? I guess I should tell the story of this, right? Because it might come out of nowhere suddenly on the channel and so on. But so last stream, I was thinking about TLS, right? And I'm going to be implementing TLS and so on. And I was saying stuff like, well, I think I'm just going to use a library or something, right? And fair enough, we might actually use a library or two for doing stuff, surely, right? But it struck me as, because I'm, at least in the last, let's say 6 years or so, I really don't like when stuff feels like, oh, that's not for me, or that's not the stuff that I should be doing, or whatever, like stuff like this, right? And I realized that, because I tried at some point to get into cryptography and all of these things, but it kind of didn't make sense. I don't know, it just feels like people doing maths over and over in your face and stuff, right? And I think that was just maybe me being a little bit, not responsive to it, to be honest, right? But yeah, so I figured, no, let's just go all in, right? And I started researching TLS, and I found this really great resource, a course actually, an entire course on TLS that also had a lot of good, solid explanations of like actually the fundamentals of security and everything, right? And so during the weekend, I have been just hardcore, actually since Thursday, I guess, I've been hardcore just effectively just studying, researching and so on security stuff, right? And I have to say I'm really liking it. I before have not been necessarily interested in this, even though I tried to get it at some point. But now I'm definitely interested. And there will be basically, I think there will be more content on the channel about stuff like this and so on, because yeah, I mean, it's important at the end of the day. It might not be, I think, you know, it's oftentimes I find it useful to find the fun in stuff, you know? And this is something where I definitely have found the fun. Even the mundane stuff, I do find kind of interesting now, and so on. And I think but I just sort of opened up to it a little bit. So yeah, 12 hours ahead of East Coast and no daylight savings time, so 11. Wow. Yeah, 12 hours that's a rough kind of, if you do want to communicate with people, that's the roughest maybe, yeah. I mean, yeah. Actually, who am I 12 hours ahead of? It wouldn't really be anyone. It would be in the middle of the sea, right? But yeah. Yeah, time zones can be a little bit difficult with stuff like this. I used to work with Americans. New York though, so it wasn't actually that bad. But I will say it got a little bit old sometimes, you know. They expect you to work their hours and so on. And you know, you end up working on something important and it's 11, or it's, you know, you're approaching midnight and you're trying to debug something with the CTO, you know, and I don't know, like, yeah, of course I care about this. I care about the project, right? But at the same time, it is midnight and I would really love to not do this right now, you know, like there's this thing that just sort of happens, and there's something, yeah, I don't know. I would say the most pronounced thing in this work relationship was actually Americans have no chill when it comes to working. They fully expect you to just put in like monster hours, I feel like. And of course, this was a startup. I want to be clear. This was a startup. We were working on contract for a startup. So, you know, they, of course, like most of those people actually had like they had money in the company. So I suppose that's why they cared so much. But then you also have to understand that we're just a contracting company from Bulgaria. We don't have money in your company. You know, we're not going to care to the same degree that you do. That's ridiculous. You know, it's sort of, yeah, it's a dangerous kind of game, this, with when people put money into companies and so on, they become a little bit, you know, there's too much incentive to destroy yourself, right? I will 100% say the CTO of that company, I would not be surprised if he cried at night. And I'm not saying that to like shame him. I mean, you guys don't know who he is or whatever. I'm saying it for real. The stress he was under, and the money man in the company he was working for was a complete asshole, like toxic, just beyond belief. And you know, like I saw one CTO before him become, you know, basically drained, right? I saw him also after that be just worn down, like, by the toxicity of this money guy and just the hours, the pressure, everything. Ridiculous. Like, this is no way to live this stuff. Meanwhile, you know, and it's crazy because I don't know. I get that people want to be part of big things and so on, but I think it's the allure of this. Oh, I could make so much money though. I think that's what actually drew people to this company more than anything, because they see like they have money bags in their eyes or whatever, right? Yeah. This whole VC thing where, well, we have around this at this point or that point, or oh well, like the money is not flowing exactly as we want, or oh, we got money, so now there's pressure from these guys to do this or that and stuff like this. I don't know. What a world. It's just it's a bit much, to be honest. All of these things, and again, I think people see money bags and they just sort of run into it. But the thing is, right? I don't know. Maybe I'm just a little bit too Spartan or whatever, or my personality is just not right for this. But I don't see the point in like, oh yeah, I could make several $1 million if this works out though. Yeah, but do you understand the odds of that are extremely low? Like, you're not probably going to, and you're gonna work yourself to death for the very minuscule, maybe, right? Yeah, exactly. This is completely correct, Max. I mean, you know this, of course, that you're correct. But yeah, this is what I think as well, at least, because of course they have just a bunch of bets that going. It's the shotgun method for most of them, presumably, right? And yeah, the irony is that they invest. A lot of them think they invest in people, but then they don't really even trust those people, is what I found also. Because there's this kind of pseudo mantra, right? Oh, you invest in people, not companies. Sure, okay, but the people in the company are good at this, but you're gonna have them do this instead. How do you figure? You know, because that's a thing as well. I feel like where they, yeah, I don't know. I don't know enough about this to criticize it within any structure, but I don't know. The whole thing just seems a little bit fucked, to be honest. And a lot of time I wonder, like, are you even better than average? Like, are you even better than random? These bets. Is there any rhyme or reason to any of this stuff? Right? And again, these people who work in these companies are like, oh yeah, I could possibly make a lot of money, so I'm gonna work myself to death, blah blah blah, all of these things. Why don't you just move to Ohio or whatever and get a house with just a normal salary, you could live well, you know? I mean, I live in Bulgaria, which is maybe the most extreme version, and I also live in a reasonably cheap place in Bulgaria. So it's like, of course, I'm saying this because that's obviously who I am, right? But I bought 2 apartments with a normal. I mean, it's a very good salary for Bulgaria. Don't get me wrong. But I bought two apartments with this salary, right? The idea that I would need, a few millions or something is just ridiculous to me. Because no, obviously not. Would I love to just suddenly have that? Yeah, but I'm not gonna kill myself for it, right? I would never. And to be fair, I just have to be completely honest and say that I have worked. At some point, I worked a lot. I worked 240 hours, a few months. So I'm not going to say like I've never done this, that only idiots would or whatever. I absolutely have worked a lot. And I got the results of that very clearly shown to me in time. The kind of come down you get after working these types of hours is ridiculous. And I do not recommend that anyone works 240 hours. It was actually 250 one month, but whatever. That's just too much. Don't do that. Even though I stepped it down considerably after, there was a whiplash effect that happened, and I lost basically all will to work at some point. So, you know, if you end up doing that stuff, you should think about, like, am I potentially risking a future here? Because it's not that your immediate health is the only thing, right? It's also your morale over time and stuff that can take a hit. And I'm not saying everyone does, of course not, right? But yeah, it's just, you know, you run the risk of destroying yourself. Yeah, this is ridiculous. Holy shit, 80 plus hour weeks. I mean, yeah, if, you know, 80 plus hour weeks, basically constant work, it's just not, it's not fine. Yeah, I mean, meanwhile, the thing is, like, starting your own company and all of these things, right? I run my own company. Is it going super well? To be honest, not really. I think I've burned through some money at this point, to be honest. Not burned through as in like, oh, this money has been useless. The only reason we have this channel right now, the only reason the channel exists is because I've taken a vacation of more than 2 months and not gotten any new contracts and so on. So to be honest, I'm fairly happy with that. But yeah, starting my own company, the irony of all of that is actually that I'm going to be able to work. I'm going to be able to provide more value to clients than I was when I was working just as an employee at a contracting firm, right? So what I should be seeing is actually a reduced stress, because they're not paying as much for me anyway, right? Because my overhead is so minuscule that I should be able to charge far less than my contracting firm was doing before, or the firm that I worked in. So basically, if anything, we should actually be much, much better in terms of stress and so on. Hello, Shaiful, again. Please don't talk about cryptocurrencies and stuff. Let's leave that at the door, you know? I don't know what you mean. What does please mean here? Yeah, I don't know. If you can elaborate, if there's a question about programming or something, I'm all ears, like I said before, right? But I just don't want to have to decipher weird sentences about cryptocurrencies being secured in Gmail or other interesting things like this. Because I don't know what you mean. Most of what you're writing, Shaiful, I'm sorry, I don't understand what you mean. But yeah, I don't know. I'm sorry, but I just I can't make sense of most of it. I'm really, really, really sorry. Well, yeah, this course that I found, by the way, maybe I should actually. So there's this guy that runs practicalnetworking.net. Oh yeah, this is actually the video that I found. Let's see. Oh yeah. Yeah, so the shared key. Oh, the shared key. Well, you can use it to. You could use it as a seed value, for example, to generate basically, effectively just. It depends on what you're going to be using it for, though, right? Basically, so depending on the algorithm that you're trying to use, you would then use this value in different ways. Actually, I don't have a clear picture of that yet. Sorry, Jay. So, for example, let's see here, symmetric algorithms. Let's see if we can just find this. Let's say we're using it with Cha-Cha 20, right? We need 256 bits, right? This is symmetric encryption, so you don't need very high bit numbers at all, right? Symmetric encryption, generally speaking, you know, the safety is fine. So let's say, okay, what do I need in order to actually do Cha-Cha 20? That's basically what we are trying to answer, right? Let's see, we do have Cha-Cha 20 actually in the Odin standard library. Init takes a context, so presumably we would want to establish a context first, right? We put this on the stack. You can see everything here is stack allocatable. It's literally just arrays and stuff, right? So everything here is a value. There are no references actually. Let's make that a little bit bigger so you can see. So you have this, right? This is our context. We init this with our init function. This is in the Cha-Cha 20 module, right? Let's just, this one. So you import core crypto Cha-Cha 20, for example, right? And what do we actually need to do here to put something in this? Let's see, right? XOR bytes is how you actually would encrypt something to a destination, presumably. It's not a well documented module, you could say. Let's see here. I can't find anything here either. Well, okay, so presumably we would use this. But where do I even put the key here? Key stream bytes. Let's look at the source because I can't make sense of the interface. Test is test. Okay, so the key stream, I'm assuming now, right? Take your key bytes. I think, okay, so technically what I think we could do is we take the value we have, the bytes of that value, and just basically feed them into keystream bytes when we have a Cha-Cha 20 context. This is you're giving me a really good sort of indication for what I need to do next. I'm going to explore this, and then we're going to do this in the next one, right? Because obviously I need to figure this out. It will be a stream much like this one, right? Where we figure out what is the interface to what we're doing and so on. And we're going to try to add to this one, right? We're going to add to this one, the code we already have. We're going to add, hey, use Cha-Cha 20 to send a message that's going to be decoded on the other side. Actually, okay, hang on. Let me see if I can. I'm going to explore this interface just for the moment. We're probably not going to do the whole thing, but we're going to try to just do something, right? I'm just going to type Cha-Cha 20 here. Most of you have probably seen me do this before. So here we have Cha-Cha 20 context, right? That's the structure that we looked at before, right? So we want to initialize this, which takes a key. What am I even doing? Why can I not read, apparently? That's ridiculous, actually. Shared secret string. I mean, I would be interested to see if this made sense. I don't think it does, though. But regardless, what we could do, so hang on. The size, the key size for Cha-Cha 20 is 256, 128 or 256, right? So hang on, just let me double check the thing here. Let me see here. The digest size of SHA-256 is obviously 256. So what we can do, okay, I have an idea, J, right? What we do is we take our shared secret, we hash it with SHA-256. Now we have our key for Cha-Cha 20, the Cha-Cha 20 algorithm, right? This will definitely work. And so what you'll do, instead of just saying, oh, I have this string, right? Instead, say that you produce the bytes like we did in the other code, right? So you can see here, let's see, bytes, int to bytes, right? This one. Produce a byte stream, right? The entire byte stream of that number, the shared secret that we have, right? Hash it, right? So hashing, of course, I'll show you that as well. Actually, is it just hash? Yeah, I think it's this one. Hashing you can do with a hash SHA-250. No, it's SHA-256 like this, I think. Crypto hash, maybe. Fuck, I don't remember this. Ah, it's SHA-2, of course. Yeah. SHA-2 is the family. So you'll do hash 256, right? On your shared secret. It doesn't need to be the shared secret string, because if you look at the signature of hash 256, hang on. Yeah, hash 256. Oh, it's a procedure. Yeah, that's why. You can see here that it takes different things, right? You can hash a string, sure, which should work as well. But hash bytes takes just a byte stream. We already know we can create a byte. It's not a byte stream. It's just a bunch of bytes, right? You have those bytes. We've already done them before, right? So we could take our shared secret here, turn it into a bunch of bytes, right? And then we run it through hash 256 bytes, I think it is. Hash bytes 256, right? Bam. Now we have an actual value, and you might be thinking, well, I mean, that's not the shared secret. Yes, we're deriving another secret from that secret. And as long as both sides understand that that's what we're doing, that's fine, right? This is our key for Cha-Cha. And because Cha-Cha expects 128 or 256, we could actually even do, we could do SHA-1 and also do that, right? but we're gonna be doing this instead. Show 256 probably gonna be better. And then we can now use this with this here. The key is the second argument to cha-cha-20 init, right? Right, and yeah, the nonce here, I would have to read up on exactly what we should be doing there. But you can also derive that as well. And then you do cha-cha-20 XOR bytes, I would assume. Key stream bytes. I don't know why we're using that. I'll be honest, like I have to play around with this, right? But yeah, because you have the shared secret, you can do whatever you want with those bytes, right? In fact, you could say, oh, the secret, the actual key is actually hashing this together with something else. For example, the shared secret together with something else, for example, right? You could initialize a random number generator with some part of this value, for example. And now, because both sides initialize it with the random number generator, we can now generate new values based on the shared secret. No one else can have that seed, right? So you can derive other secrets from this secret, basically. That would be the actual strategy. So in some sense, you've established a secret that can produce other secrets, right? And of course, the whole idea, just to be clear, the whole idea of actual security is like, even if someone has your code, they should not be able to break it, right? So it's not necessarily useful to be like, oh, we're gonna hash it 2 times and no one will know that. You could do that, and you would get some extra security because people will not figure out that you've hashed your secret and then hashed the hash together with some word and so on, right? Necessarily. But yeah, this is not real security. It's called security by obscurity, generally. But yeah, you do have a secret that you can derive other secrets from, though. So the security of that secret gives you the security of, doing everything else. So yeah, like I said, to do, turn the get bytes from shared secret. Actually, I'm gonna put this down here. 2 hash bytes with SHA-256. Use hash as key for cha-cha-20. Yeah, I absolutely. I think it's the first thing we go to as human beings is like, what's the absolute easiest way around this? The easiest way is not math, right? Or like, hey, this is a robust algorithm. The easiest way is like, what if we make every other letter in this string? Like it's something silly like this that, yeah, once people have your code, they're like, I mean, it's dumb, but, they can see what you're doing, they can figure it out, and then they can just sort of break what you're doing, right? But yeah, I think we all have this moment at some point while learning stuff like this, that, well, what if we do this thing that no one could ever foresee that we're doing? Yeah, sure. Yeah. I mean, it's basically like, if your cryptography scheme relies on it being secret, right? The whole scheme is in some ways a password, right? You better hope that the scheme itself actually uses real security, otherwise you're done, right? But yeah, Jay, did this make sense, what I was saying? I hope he didn't leave. because I did have this moment of insight that I wanted to share. Because yeah, it's we can absolutely take the shared secret. Yeah, okay, so you're okay. Yeah, we can take the shared secret. Like we get the bytes from it, we hash those with SHA-256. That reduces the actual secret, right, to 32 bytes. We use that hash for SHA-20 as a key, and then now we can encrypt and this is basically what I'm gonna do, what I'm gonna be trying out. And I might be trying this out before tomorrow, but if I haven't, we'll do a stream where we do this. Otherwise, the stream will start with me showing this, I guess, right? And to be honest, I don't foresee this taking a lot of time. Like today, I was like, oh, I'm probably not gonna get it to work immediately, whatever, right? This should not be a massive problem at all. So we'll start out the next stream doing this, or I will have already done it because I was curious or whatever, right? And then we're gonna try to kind of move on to other stuff. I'm gonna have to fill the stream with other stuff, to be honest. I don't exactly know what we're doing yet. We might try to do, yeah, I'm not sure, actually. We'll see. I want to play around a little bit with the APIs that we do have access to in Odin to some degree. I don't know if you guys have noticed, but in the packages, we actually have in the vendor packages, we do have a cryptography library. So we have this Botan, right? And Botan has a bunch of stuff, in fact, that you don't see in the upper layer, but it has a bunch of things, right? So what we can actually find here that we have DSA, right? Digital signature algorithm. We have RSA, right? And we should have EC DSA, for example. This is very modern, very actually up to date, and so on. This is elliptic curve cryptography, fucking super science stuff, you know, and so on. So we have a bunch of stuff that we can actually, you know, potentially we could use. I'll be honest though, when I'm looking at these interfaces, I don't understand shit, you know, because it's like, yeah, I don't know what to say. There's just a lot, and all of it follows a certain interface, and I haven't figured out what that interface actually is yet. So I want to look more at these things because we do have access to things. At some point, we're gonna have to deal with some of these things. Here you have certificate stuff, X509. This is actually the certificates you use for TLS. And so on. So that's also something I'm gonna have to look into, certainly. Here you have block cipher. So whenever you're using a block-based cipher, which should be, I think, most of them, I guess you call block cipher encrypt blocks. Block cipher struct. It's just a struct that's empty. What? Oh, I see. Block cipher T is a pointer to void. It's a void pointer. So you're passing a pointer to something, in fact, when you use this, right? Right, okay, this makes sense. So it is an empty struct. It's there only for its name. When we use this in block cipher encrypt blocks, what we're actually supposed to be passing here is one of the configuration structs that we have, right? So we saw when we were loading, let's see, pub key load, etc. Let's say this one, this priv key struct, and so on. This is the actual structure, I think. Maybe not. but it uses opaque values, right? So it uses basically opaque pointers, void pointers, this interface, because presumably it's just C. And so what we would have to do is just figure out exactly what we need to do, because we have to create the structure, and then we have to basically say, hey, take a pointer to that structure. That's what's going to be passed in to encrypt blocks, and so on. And we'll be fine. Hang on. And then you get to bcrypt, and it's like, oh, this is just straightforward, nice interface function that does stuff, right? With the exception of maybe the RNG struct, but that's probably just an RNG, like this is a random number generator you're passing. Yeah, I'm not entirely sure. Like, we would have to explore some of these things, right? I do think, obviously, we're not going to the vendor package immediately. We're gonna stay in the somewhat more reasonable world of just sort of, you know, Odin cryptography modules, right? And then we're gonna look into the others, basically. And yeah, intent documentation is definitely something that Odin is missing even in its own standard library, right? It's not even the vendor packages. The vendor package I can understand, right? But even the normal ones are, most of the ones that I'm interested in right now have shit for documentation. Like, it's just nothing. Just like this mess here. What am I supposed to do, guys? Like, it just, yeah. All right. Yeah, I'm gonna go as well. It was a good stream. We got the thing done, which I was super happy with. We actually did the thing. It went well, and I'm really happy that, you know, we could get this just sorted out, basically. And yeah, I will see you guys tomorrow, hopefully. The stream might be a little bit later, so it's possibly just better for people's time zones or whatever. I don't know. I don't know. It's also Monday tomorrow, so it doesn't really matter. But yeah, that's it for today. And have a nice day.